Welcome to Wolf Code, where we hunt bugs and write epic code.
Welcome back to Wolf Code, your favorite DevLog channel. Today we will do a recap what we have done last time, which was the problem we are dealing with, also which is the solution we are coming with. So stay on, hit the like button, the subscribe button if you haven't. First of all, let's do a recap with our program, which we had before. So let's look up at this road. We have some addresses added on. We have A, B, C, D, and E. That's perfect, right? We are going from A to B, from B to C, from C to D, and from D to E. That's perfect, right? That's perfect. If you go on the same route next day, and maybe your boss says, okay, if you have these stops, you can add another one. And I say, no problem, we are doing that, we make some money, and that's not a big deal. So, we have to place a new address. Let's say the new address is named P, which is here. How our route calculates if P is near one of our addresses to be added on? So to integrate that new address to the route. If you are looking, we are going from A to B, from B to C, and then from C to P. Okay, that's perfect, right? But our program doesn't do that. Instead, it calculates using anchors. Each address can be an anchor. For example, A can be an anchor, B can be an anchor, C can be an anchor, and so on. To calculate if the address is enough near to an anchor, we have to use two anchors. Okay, let's say we use B and C as an anchor because it's enough near to P, which is the new address. Okay, let's say the distance between B and C is around 80 meters, right? And from C to P, it's around 100 meters. And from P to B, it's around 50 meters, right? Right, because it's not a big deal. So, let's move on to calculation. To find out if the new address is enough near to our anchors, we use a ratio. If we have a ratio between 0.5 and 1.4, that means the address is enough near our anchors and we can add the anchor between. So let's move on to the calculation. To do that, we have to divide 80, which is the distance between the anchors, by the distance between B and P and P and C, which is those one, right? Okay, we will have here 150, right? Divided by 150. This is perfect, you can say, right? So, if you look up, we have on both sides a 0. And because 80 is less than 150, we can simplify it. And we want that. Because we have also a 0, both of them are divided by 10. That means here on the side we can have 8 because 8 multiplied by 10 it's 80. And 15 multiplied by 10 is 150, right? So we have 8 and 15. That's perfect. And now we look up how many times those 15 goes in 8. 0 times, right? Because 15 is bigger than 8. That's not a problem. We'll add here and 0. Now we have to take down 8 and add on 0 because we use decimals. 8 and 0. We have the same number as 80. Okay. How many times does 15 goes in 80? We do a calculation. 2 times is 30. 4 times is 60. That's perfect. we have another 20. So 5 times and 75. That's perfect, right? 5 times. Now let's look up. We add here 75 because just because we have here a 0, we couldn't make 0 minus 5. So we take 1 from this, from 8. We take 1 decimal from 8. So we have to do 10 minus 5, which is 5, of course. So now 8 becomes 7. That's more like a Z. Let's do a 7 properly. Now we have 7. And 7 minus 7 is equal 0. Okay, because we use decimals, we have to take 5 down and another 0, which now is 50. And how many times does 15 goes in 50? If you look up, 30 is much less than how many times can goes in 50, and 60 is too much. So it might be 3 times, which is 45. 45, right? We do the same calculation. We have 5 again, we have 0 again, and so on. We can continue this calculation, but because it's infinite, we don't need to do that. And also, we need just the first 2 decimals, which is 53, which are the best numbers between 0.5 and 1.4. Her ratio of 0.53. That's perfect, right? Now, because we know P, let's use another color. Because we know P, it's enough near both B and C, we can add this address between. And the order will be A, of course, then B, of course, because now it's between, it's B, C, D, and E. Why is that? Because our program, it just knows how to add the address between. It doesn't know how to sort it out, how to add it after C, for example, this one. It doesn't know that. So our problem is to solve this and make the computer think how we can add the address after C or before B if it's really needed. To be here maybe. Not after, maybe there. Who knows? So let's move on to see which is the solution we have found in the first. Let's do another round. Let's use another road, of course, not that because it's used. Let's say we have a road coming up from up to down. No, that's a little bit thicker. We have a road coming up to down, and then we have another road, which is here, right? Perfect, you say. Another road here, another road here, make another road here, and so on. We have made a bigger road, for example. Now we have to add some addresses. Let's use red for the addresses. We have here maybe Motina. A can be added here as B, here as C, and D and E. And the new address we should be added here as P. And to solve this problem, you saw that the order to do that is A, B, C, go back P, D, and E. That's perfect, right? This is the order we want. But because our program doesn't know to sort it out and in which order to goes, the program does A, B, P, then go to C, back, D, and E. You see that? It goes on the same road twice but also it reversed here. And to solve that problem, we have to use triangles. Yeah, you heard, we use triangles. And we can make from 3 anchors, A, B, C, and triangle, right? Okay. Okay, so we make a triangle. Because we have those A, B, C. We have B and C, which have to calculate if the address is enough near, but we have to solve that problem, which if the new address is after those sections, to be added after, not between. So, we calculate the perimeter here to this triangle, right? We have to calculate that. And in order to find if P is enough, it's outside this triangle or inside. And to do that, we need to have another 3 triangles. We use another color for that. For example, a new triangle should be A, which should be B, C, P, and B. This is another triangle. Okay, another triangle should be A, C. Let's use another color for that, I guess, to be much more nicer. Okay, A, C, P, and A. This is another triangle, for example. Now we have 2 triangles. We need another one, the third triangle, which is BPA. Yeah, this is another triangle. Is B. Let's use another color. I have forget. Let's use. It should be B to P, and then from P to A, and then from A to B. This is another triangle. It's not like a normal triangle, but it's something like we have to calculate the path. If we calculate each area of these triangles, we have 3 areas, which we have to add it together to make it one. If that one, we do the final triangle area minus the first one, which is ACB, first triangle area ABC, minus tolerance, which can be tolerance equal with 0.00001. If it's less than 1, then it's inside. The new address it's inside. But if it's more than 1, more than 0, not the 1, it's outside. Now because we know P, it's outside of this section, we have to decide if the P is after C or before in this section. To do that, we have to do some calculation, which the calculation is, we have to do one time BC multiplied by BC plus BP multiplied, not BP, multiplied by BP, of course, minus CP multiplied by CP. Everything we have to divide by 2 multiplied by BC multiplied by BP. And if the number is less than 0, then mean is before P, is before C. And if the number is bigger than 0, then mean it's after. Now, because we have a solution, we are coming back next time with this